So I wanted to change a little bit the presentation. You have seen a lot of hydrogeology, but one of the big problems that we face when dealing with geoenergy is this induced seismicity. And this is pretty much linked to hydrogeology, but when we look at models, what do we really need to understand from hydrogeology? What do we really need to model in the end? We have seen very fancy models with many fractures. We have seen models doing very detailed pore scale modeling. But what do we really need to know with respect to seismicity? Induced seismicity is basically everywhere. Whatever we try to do to produce energy from the deep underground, we can have induced seismicity. Of course, hydrocarbon extraction or injection activities. If we do sequestration, shale gas exploration, geothermal, even hydrodams can induce earthquakes. Just a few examples. This is the very well-known case of wastewater injection in Oklahoma. This is basically where the entire study, these many studies that have been published in the latest 10 years, more or less, these have been triggered by this problem in Oklahoma, where they started to see a huge increase in seismicity with respect to the background level for magnitude 3 and above since 2009, more or less. Of course, there are other cases. There are still ongoing cases. One of the latest is this debated case of South Korea in Pohang. So they were just trying to produce that geothermal system, an EGS system, and they had an earthquake of magnitude 5.5 that strangely occurred after 2 months after the operation. If there is time, I will give you some more details about this, maybe in the discussion later on. And even teeny tiny Switzerland has its own cases of induced seismicity. You probably know the case of Basel. It's very well known. It was more than 10 years ago. It was in 2006. But there was also this other case of St. Gallen, which I will show later why we should care about these kind of cases. So this is just a map of the seismicity that has been linked to human activities. So you may recognize the case of gas extraction, the very famous case of Groningen, or all the induced seismicity in Oklahoma. And I guess also this one very well correlated with the lights, as we have seen in the other talks. Because we have this induced seismicity where we need energy, basically. And this is where we also have light. So this will correlate also, as I'm sure it will correlate very well. And can you guess what's the percentage of activities that is leading to seismicity? Just consider all the possible way we have to produce energy. What do you expect? 50%, 20%? All of the activities will produce seismicity? Good, 80. It's actually 85. So if we look at all the possible, I'm just listed these in just try to collect all the fossil energy, and I'm classifying as all the other kinds of energy like solar, like wind. And I'm considering nuclear only the production of energy. I'm not considering the extraction or nuclear rocks. So if we list all these, then we get with 85% of the way we produce energy can also produce seismicity. So it's a problem that we really need to face. We really need to understand how we can avoid this. From a scientific point of view, it's very interesting to work on induced seismicity because it's very challenging, and it's also kind of linking not only science, but also population and regulation. We need to face also the social acceptance of these different technologies. One thing that we need to say is that most of the time we want induced seismicity. We want the microseismic events to enhance permeability because we want, maybe especially for geothermal, for example, we want to enhance the permeability in our system because we want to have a better circulation, we want to have more fluids, we want to produce more hot water. So we don't need just to look at the number of the induced event. We should also try just to understand how can we reduce the maximum magnitude, for example. And in theory, this should be possible because we know where we are changing the condition. So this induced seismicity can be somehow controlled. And there are several examples in literature where they just switched off the injection pump and the seismicity stopped. Also, we know the location where we're doing the operation. And what this means, that we can also get much better monitoring. We can instrument, we have seen also here that monitoring techniques are getting better and better. So we can try to use everything that we have available to try to constrain this induced seismicity. We should try to understand when we want to stop it, how can we do that? And of course, it's very interdisciplinary. It's not just seismology, it's not just hydrogeology. We need to know the geology of the place, the region where we're doing. We need to know a lot about exploration geophysics. We need to know about rocks physics. And as I was saying before, it's also related to social science. And more important, when we relate to induced seismicity, we need also to relate to operators. And this is the question, the relevant question that are always asking. They don't care about what is the physical mechanism that is inducing the earthquake. They care, is my operation safe? How can I reduce the number of events if the population is complaining? If I'm continue doing in the way I'm doing now, I'm seeing that I'm recording seismicity. Is the risk for a larger event increasing if I continue as I planned? Can we find other alternatives? This is the question that we should try to answer. So yes, as Peter was saying in his talk, science is very important and it is the base for all this, but we need to comply also with operators, especially when dealing with geoenergies. And one of the basic things that is being proposed to deal with induced seismicity is the so-called traffic light system. And the very simple one has no physical meaning, there is no uncertainties, nothing considered, it's just like a sort of threshold. We see an event of magnitude 3, magnitude 3.5, we just decide to stop the injection. So we can have a green, red light depending on the events that we observe. But with the advancement of big data, of these machine learning techniques, we should be able to move to an adaptive traffic light system. We should be able to combine modeling, real-time observation, real-time risk assessment, so to create this adaptive traffic light system, this ATLS, that are changing, dynamically updating based on the conditions that are being observed at the given site. So this is just a sketch on how a possible traffic light, advanced traffic light system may look. So we have like our real-time data acquisition. The model should be able to read this real-time data and to embed this in model, and then we can have synthetic seismic catalogs that we can compare. We can calculate the risk associated with what we are observing. And as you can see, modeling is playing a pretty big role in this. Modeling. So if you look in literature for some hydromechanical simulators, there are plenty of them. There are porous medium coupled simulators. There are, as we have seen, for DFN fracture models. And there are also some other models that are more into really the fracture propagation, so for hydrofracturing. And this is for sure not quite extensive list. There are many more that I just forgot to add here in this list. Of course, I've been in Berkeley for quite a long time, and so I'm kind of used to play with these TUF2 codes. So in this, for hydromechanical problems, we are linking the TUF2 code with this FLAC3D and Itasca code in a implicit way, sequential implicit way. So we have some of the variables that can be changed directly, as we, for example, the porous change, the pore volume change. Some other variables are just calculated indirectly, so like the permeability, the change in capillary pressure, or like we can just relate this permeability, this porosity, to what we observe has changed in mechanics, like the mean effective stress or the volumetric strain or even plastic strain. And I just want to show you a little example that is related to the carbon geological sequestration. So one of the big questions for CO2 sequestration is that is safe in terms of seismicity. So far, we have not observed any big events associated to CO2 sequestration. But it's interesting from a scientific point of view, just to understand if the physics is saying something, what we can expect if there is a fault zone in our reservoir. Is this getting reactivated or not? What kind of pressure do we need to reach to reactivate? So in this very simple example, we have like this 100-meter storage aquifer bounded on both sides by a very low permeable cap rock, and we have a fault zone that is cutting through the reservoir and through the cap rock. So this fault zone is here modeled as a fault with solid elements in which we can change the permeability as a function of the normal effective stress, the normal stress to the fault, in a sort of very similar to the Bandis equation. And we can also link this to plastic strains if some reactivation is occurring on the fault. So this is a very simple, very synthetic case, nothing really related to reality. So we just inject CO2, it's 500 meters away from the fault, and then we observe some pressure that is increasing. These are just some plots on the fault itself. So we see the pressure is increasing. We see that our stress is changing, and so we expect reactivation to occur when the failure criterion is reached. In this case, just a very simple Coulomb failure criterion. So we have learned from Michael, from the talk by Caroline, that how these fracture faults should reactivate. So can you guess where the fault is reactivating? Where is the point where we should expect reactivation? It's like everywhere where we have high pressure, it's just top, bottom. Can you guess it? You got top. Someone says bottom. You got bottom. And why bottom? Why top?
Normal stress is lower at the top.
So if you look at this, the effective stress here is lower. So it's that where you should actually get reactivation. But I will just argue that it's at the bottom, because the shear stress is changing as well. Because we have deformation, so this deformation can accumulate also on the fault as a form of shear stress. It's just that dilation of the reservoir. So what we actually see is that the point where you reach the reactivation is actually at the bottom. And this is why, because we have poroelasticity involved. As Michael explained, all this poroelasticity, pressure, and stress are linked. Deformation are always linked. So this is one of the big mistakes, or I'll just not call it mistake. It's one of the biggest approximation that most of the people working in induced seismicity are doing. They just assume that the fault zone has a stress. They just subtract the pressure because they want to calculate the effective stress. And so they may get a value of pressure required for reactivation that is much larger than what you really need. And then, of course, when you talk about seismicity, we also care what happened after the fault has been reactivated. We care, it's not just the point to reach the reactivation. We care about what happened when there is the reactivation, because we care about the magnitude. We care about the ground shaking. And so what we do here, we just assume this very simple strain softening model. So we're assuming that there is a frictional law on the fault. So once we get to the reactivation, the frictional coefficient is just moving from the static condition to the dynamic condition. This is very similar to when you have a block sliding on an inclined plane. If the block is still on this inclined plane, you have a frictional coefficient. And when this block starts moving, you have a coefficient of friction that is lower. Of course, you cannot just pass immediately from static to dynamics, because otherwise the energy is not conserved. So you have very often to assume that there is some change. In this case, we assume that this change is linked to the plastic strain that is associated to this deformation, to this reactivation. And so what we have, if you look at the change in normal effective stress versus change in the shear stress, what we see is that when we reach the reactivation, our stress has to change to the dynamic value, and we get so-called stress drop. And then this stress drop can just, let's say, propagate on the fault. Even if you look just at the quasi-static case, this is just quasi-static case. There is no dynamic involved. We are not simulating the seismic wave. It's just for mechanical equilibrium. If there is one point where the stress is dropping, this stress drop has to propagate on a ruptured zone. So in this case, we are able to simulate the earthquake that has rupture on this length. And of course, then we can play around and say that we know that we have a slip that is associated to this reactivation. We have a rupture length, so we can easily calculate our so-called scalar seismic moment that is linked to the seismic magnitude that we can expect. So in this particular case, we see that we simulated an event of magnitude 2.7, which is quite large if you think on induced seismicity. This is already something that can create some concern in the operators. In the particular case of carbon sequestration, we also care about what happened to the CO2. Is this moving to the fault? We have seen in Michael's presentation that the permeability is changing quite a lot during earthquakes. So what happened here on the same fault zone? Do we expect the fluid to move faster just because of the reactivation and then to create some pathway for the fluid to escape? This is true for carbon sequestration, but this is also true for any kind of storage. When we do some storage, you want to keep the gas there or the fluid there. And so in this particular case, we have a permeability that is very high at the beginning, so we really get a huge leakage into the upper aquifer. And if you look at the safe threshold that have been established, you see that we are quite off. And you can also play around and try to understand if there is a link between the leakage that we observe and the magnitude of the simulated seismic event. And this is what we have done here. So we see that we have leakage only when we have a relatively high injection rate and high initial fault permeability. This is very normal. If the permeability of the fault is initially very high, you don't even need an earthquake to have leakage. What's quite interesting is that when we see the largest event, this is not correlated to high leakage. One of the reasons for this is that we are modeling a normal fault, so most of the change in permeability or the slip is going down in the bottom part of the caprock. So the upper part of the caprock is not really much affected by permeability change, only minorly here. So that's why we don't see pretty much the leakage going up. And I'll just recycle one of Michael's figures that is just relating injection and production induced seismicity. This is a very simple way, a very elegant way to describe the difference between the two. In injection induced seismicity, we expect the stress to change, the effective stress to change, to increase up to the strength. In this other case, it's the deformation that is playing a major role. But in most of the case, I would just say that it's happening both at the same time. It's just the same exact physics, but just at a different timing. So we have used the same exact model. Actually, it's slightly different. In this case, we have a compartmentalized case. But this is exactly the same model to try to explain the production-induced seismicity. So we have the production. We have quite a lot of shear stress change. This is how the normal effective stress looked like before the reactivation, and then in the same case as before, we get reactivation, and then we can simulate the seismic event. And this pretty much depends also, the time evolution depends on how many wells you have in your system. If you have only one well, if you're producing from both compartments. And also we try to play with some recovery activity. So what we have to do, what happens if we stop the production? Well, some of the case is just returning to the original case, but depending if you are producing or injecting in one of the two compartments, you may have quite different scenario, and then you can actually get to the reactivation even if you stop your activity or if you inject to prevent the deformation. Of course, we can learn much more. We can play around with this model. We can extend it to 3D. We can add heterogeneities on the fault. We can also play with the dynamic. We can try to simulate really the seismic waves. We can try to add more complex friction laws. We can try with the hydrofracturing, hydroshearing. And with synthetic models to study the physics of the process, you can go ahead and publish paper for years. And I've done that, so I guess it can be done. But that's not really what we need for traffic light system. For traffic light system, we have many earthquakes. We don't just have one earthquake. And most of the time, especially for EGS, it's not really nice to simulate that as porous medium. We have seen examples, EGS, geothermal reservoir, pretty much fractured. But if you go 4,000 meters depth, and we want to simulate this with the porous medium, it's just not going to happen. Of course, we can play with DFN models. This is a very nice example that was just published by this group in Stanford, where they played with this stimulation at Fenton Hill, and they are trying to determine which is the correct mechanism that led to the seismicity and to the permeability change. And I think they are doing a pretty good job in trying to reproduce the seismicity that was observed. But is this really what we need? When we have a discrete fracture network, it starts to be complicated to understand which is that is causing that seismicity. If we have all these models solved, all these equations solved together, it's quite complex to say which is the component that we should play with, that we should tune with to have less seismicity or to prevent a large events to occur. Of course, we don't really know where are the position of all these fractures. Maybe just the big ones that are cutting the well. It's not like in the underground labs where you have all these tunnels where you can map all the fractures. If you go 4,000 meters depth, you have probably just one well. It's really hard to determine where are the fractures, how big are these fractures. Of course, we can still play with it and use the very nice probabilistic approach that we have seen before. But then it starts to be quite computationally expensive. And when you want to deal with traffic light system, you don't want just to run one single simulation. You don't want to just simulate one simple realization. You want to simulate several possible cases, several possible things that are happening, and you want to simulate that every time, day and night, possibly. So this is not really going to work with DFN because it's too complicated. And if we then, something like St. Gallen is happening where we have some gas phase that is involved in the simulation. So in St. Gallen, what happened is that while they were just doing some injection test, they got some gas kicking out of the well. And to prevent the explosion of the well itself, they had to proceed with some well control measure. So they had to inject mud to prevent the gas from escaping. And how can you model this with a discrete fracture network? It's way too complicated. It's way too computationally expensive. Of course, we can wait 10 years that we have better computers. Maybe we will be able to do it. But GeoEnergy is something that we need now because it's something that we face every day. But we can play around to that. So we can try to learn something from fully coupled models. We can use seismological, for example, statistical models that are quite good in predicting the possible regions where we have seismicity, in natural seismicity. And we can create the so-called hybrid models that are mixing some statistical approach with some physics-based models. So at the SED, we have been working on this quite long. I just took this that was already developed. I just had my ideas to have some TAF2 models in it. But this is a process that we are trying to develop to have this fast code that are approximating at the best as we can the relevant process for induced seismicity, not all the physically possible processes. So this is just one example on how we can do it with permeability change. For example, with this stuff sheet, we can have some permeability change that is reversible, just linked to the pressure change. We can have also every point of this that is actually changing the permeability because we can associate every single point of this to a fracture, so where the permeability can actually change and where the fluid can propagate. So we can change the permeability in the nearby region linked to what we simulate as an earthquake. So we can just assume that this point is reactivating and we give it a magnitude based on some statistical seismology. And with this kind of model, we can also try to understand which physical processes are relevant. For example, in this case, we're just trying to understand if the stress transfer, so what Michael was trying to explain before, the interaction between the different earthquakes that we are triggering, if there is an interaction between these, if this is changing the condition in our system. And so this is what we're trying to say, to study here. So we see that when there is stress transfer, of course, we expect more events to occur. And more of this, most important is that these events are far away, as not just where we have pressure, but can occur also in regions where we don't have pressure changes at all. It's just a little example of now you can apply this to Basel. I didn't do a very nice job here with proper inversion. It was just trial and error, just to get some good solution matching some observation. So this is, we have not just one single simulation, but we are running a number of realizations, so we can just do the average and try to match the average. Too much. Just the average with the observed, for example, in this case, pressure, or with the observed seismicity. And of course, in this way, we are also able to simulate in a simplified way the case when we have two-phase fluid flow. So in this case here, we are simulating the gas kicking. So in about 1 day after they started the operation, we just assume in our conceptual model that some clog in this gas pocket was reactivated by the initial operation, and then the gas just started to fluid up into the well. And then when they inject the muds, they just cause some seismicity. And we can also try to understand if the gas was important or not. And so this is what then the operator wants to know. Was the gas that caused the earthquake, or was the water that we injected? Because this changed quite a lot if you have to think about insurance for these companies. Of course, there are other approaches to simulate hybrid models. So this an example by Seagull, that they are using this fancy rate and state model to have induced seismicity, or this other example by Dietrich that I will call it the father of rate and state, where in this case they are using a very simplified pressure model, but a very, very complex model for seismicity with the boundary elements code. And this is something that we want really to aim in the end, to have some prototype of traffic light system. This was done recently by this PhD had in our group, where she just tried to combine different approach, just only statistical models, trying to use some hybrid models, or also doing some ensembles of these different models. And what she showed is that if we take the example of Basel, where we take only a portion of data, what we call learning period, and after this learning period, we continue to simulate in our system the same procedure as they've done in Basel, you can clearly see that the probability of having a magnitude greater than 4 was already there. It was really there. And this is another approach how it can work. They say that at the end of your learning period, you just stop the injection and see what happened. And this is what this traffic light system could really work well in saying that, okay, if you stop right now, the model is predicting that you will never get, or we have a very low probability of getting a magnitude 3 event. And only if you go to a larger injection rate after 5 days, you start seeing that the probability of having a magnitude, an earthquake with magnitude greater than 5 is increasing. So we just conclude here. As I promised, I was very fast. Try to stay in my 30 minutes. So what we need to do in terms of modeling for traffic light system is that we should always remember that induced seismicity is a multidisciplinary case. We need a multidisciplinary approach to really deal with it, to try to understand the physics and to try to prevent the bigger events. We cannot just live with sophisticated models. We need to combine probabilistic and deterministic approach. Otherwise, we will never be able to predict it. Our prediction will always be too deterministic, and we cannot pretend to know everything that is occurring at 4 kilometers depth. Of course, we need to have models that are learning from data, that are updating based on what we record at the given site. And of course, we need real application. We need more underground labs, projects, to try to test this prototype application, and we need more pilot tests before we can really go to the to the larger scale. And with this, I'm done with the presentation. Of course, we can continue the discussion as is planned in the schedule. And if the case, I can also show you some more examples of real case of induced seismicity. Here I was just pretty much synthetic, I would say. Thank you.
You say your approach is therefore kind of experientially based rather than predictive?
It depends. If you're the approach will be experience-based if you're able to learn from the data in real time, which is another bottleneck. I mean, currently we are not really able to get all the data in real time. Of course, we can learn, we can get the pressure from the well, we can get the seismicity, but precise location, for example, is a big problem. We are not really able to get precise location in real time. One other important thing that we are not yet able to do it is understanding the orientation of this fault zone as these are reactivating. Because as a matter of fact, we don't know how to get a so-called focal mechanism, especially for small events. In real time, it's even more complicated. So the ideal case is to go for an experience-based code that is really learning from data. But right now, it's still based on prediction. Most of them, most of the codes available are just predictive.
You say predictive, it means that it's based on modeling. I mean, I don't understand. You have a lot of data on the seismicity.
But your goal is not to, I mean, of course, if you want to study why something happened, induced seismicity is a gold mine because you have a lot of data, as you said, but that's only after. You want to be predictive before all this seismicity is happening. You want to understand before it happens where it will happen and with which possible, with more or less with which magnitude, or if it is going to be a large magnitude. One example in Basel. In Basel, of course, it was 2006, so it was 10 years ago, and techniques for monitoring have changed quite a lot. But in Basel, it was, if you look at the very well relocated seismicity, it's quite clear that all the seismicity was aligned on a big feature. Big fracture, big fault, don't want to enter in that discussion. But if you're able to say that, hey, wait a second, the seismicity is aligning on a fault, so maybe I can expect a larger earthquake to what I'm currently monitoring, because I'm having a larger feature that is getting reactivated. So the probability that this feature will have a larger rupture is increasing, because probably also the fluid is just moving toward that fault zone and then reducing our effective stress and create a bigger earthquake.
Can you tell us a little bit what happened in Korea and with, if I'm correct, an earthquake induced several days after the injection?
Several months.
And do you think that such approach would predict that, or is it quite an extreme case?
Then I'll just move to the next presentation. Okay, South Korea is not that much seismic region as the close Japan. So there have been some earthquakes, and it's actually kind of occurring in swarms. They had quite a lot of seismicity in the 1600s, and they started having a lot of seismicity now. So there was this Jeonju earthquake in 2016. So it was more or less when they were already playing with the EGS. The EGS operation started in February 2016. And then there was the Pohang earthquake. It was last year in November, which was much, much closer to the EGS system. So what we did here, I mean, there were two actually papers published at the same time. So one that I called, it's the paper that we published, I call it European paper. So we didn't have access to local networks, so we just look at the regional seismicity. We took station from all over Korea, from Japan, and we tried just to have some analysis of inter-ground uplifts just to check if what we were relocating as seismicity was in agreement with what you will get from the insert deformation. And then there was the Korean paper that was published on the same issue that is actually analyzing data from a local seismic network, so much better data to really understand, to have a proper location. And they also had the opportunity to correlate this earthquake with the net injected fluid. So this is the insert. So this is the location for the EGS system. This is what it was observed in terms of deformation. And this is what our very simple model, we didn't do any fancy inversion. We just used a very class-based inversion. This was Andrea Manconi from ETH. So he just placed a fault zone here and just tried to model the displacement of this fault zone, displacement, opening, and then he was able to have the same kind of deformation pattern. If you looked at the relocation of the seismicity, it was very easy to relocate the major events, but we also had the opportunity to relocate some of the aftershocks that occurred after this seismic event. And what we see, one of the most important things that we see is that most of this seismicity, although we have very big error because we were using a regional network, most of these events were located at a relatively shallow, about 4 or 5 kilometers. And if you compare these events to what was observed the year before, 20 kilometers south from the EGS, we see that there's a quite difference in depth. And of course, this seismicity is very well in agreement with the modeled fault zone from the insert. We also tried to play with Coulomb, saying, okay, what if this earthquake was just triggered by the earthquake the year before? And what you see, yes, maybe we can have some positive Coulomb stress change. So this means that the 2016 earthquake can have some little effect on the 2017 event. But if you look at the value that we recorded here, is of the order of 10 to minus 4 megapascal. As Michael was saying before, I mean, it's well possible that this is still having an effect, even if it's very small perturbation. But more important is what could be this earthquake, the effect of this earthquake on the much larger fault zone that is nearby. And then there was the Korean paper that, as I say, they had a much more dense seismic network, very local. They were actually monitoring just the aftershock in the region 20 kilometers south. And then while they were doing this, they were observing some earthquake occurring north, 20 kilometers north. So they just decided by chance to move all their seismic network, these 30 seismometers, in the northern region. And this is when they were able to record this Pohang earthquake in November. And if you look at the relocation, this is very well in agreement with what we have found from the regional network. And apparently from this location is very, very close to the location of the injection wells. And then if you look at the net volume, they see that there is, of course, quite a lot of correlation with the observed seismicity and the injection operation. But they are claiming that, I mean, one of the issues raised is that the volume, if we look some literature values for the maximum magnitude related to the volume, for the net injected volume, they are just claiming that the injected volume was not enough to trigger a magnitude 5.5. Of course, this is still quite it's quite in debate. We don't really know if this was induced, trigger, or you want to call it. I don't make a distinction between induced and trigger. For me, they are just the same meaning. But of course, people are in the scientific community. They always want to distinguish between induced events, which are the events that all the energy that you have created by injecting is released by the earthquake. Trigger means that there is some pre-energy, and all the energy, this energy was released by even a little bit of alteration because of human activity. So I don't like this distinction because for me, just it's very narrow line. It's not, I cannot just draw a line and say, no, this is induced, this is triggered. So I don't make distinction on that. But there is quite a big debate, and that actually there is a committee in South Korea that is now investigating on this, trying to understand if it was really linked to the human activity or not.